Going to be working here on the homework for 8.1. It's the section on sequences. And this is off of page 434. So let me start with number 5. I want us to find a formula for the following. So we have negative 3, 2, negative 4/3, 8/9, negative 16 over 27, ... All right. Well, the first thing I'm going to notice is that we do have an alternating sequence. We have starting with the negative, then positive, negative, positive, negative. So in order to make that happen, I'm going to use what we did in class, negative 1 raised to the n. So if I replace n with 1, I'm going to get negative 1 to the 1 power, which will give me negative 1. So that times something else will make sure that we get a negative. And then when n is 2, we'll get squared, which turn this into a positive, then negative, then positive, and negative. So that should get us the alternating sequence that we need. And then I'm going to focus on the numbers. And the first two numbers are kind of tough to see what's going on here. So I'm going to look at these fractions instead. And I'm going to try and come up with a way of generating the numbers on top and then a way of generating the numbers on the bottom. So it looks to me that this right here, this 4/3 can be written as 2 squared over 3 to the first power. This looks like 8 is 2 cubed and 9 is 3 squared. And then 16, notice I'm not worrying about the negative because I already took care of that. This next one, it looks like I've got 2 to the 4th over 3 cubed. So that looks like the pattern. Let's see if it works if I go backwards. If I go here, I would have to have 2 to the 1st because it looks like these powers are increasing by 1. So if I go backwards, it's got to come down by 1. And that means this will have to be 3 to the 0. Let's just double check this. 2 to the first power is 2. 3 to the 0 is 1. 2 over 1 is 2. So that does work. And if I follow this pattern, it's got to be 2 to the 0 over 3 to the negative 1. Again, coming down by 1. Let's check what this is. 2 to the 0 is 1. 3 to the negative 1 is 1/3. And if I do 1 divided by 1/3 and flip it, I get 3. And of course, the negative was already taken care of. So that looks like it. So my first term of my sequence, or the first number in my sequence, must be 2 to the 0. So when I plug in 1, I need to get a 0 up here. Then when I plug in 2, I need to get a 1. And then when I plug in 3, I need to get a 2. So notice that the powers here, 0, 1, 2, 3, 4, those are just your counting numbers. And we need to start it at 0. So the top is going to be 2 to the n. That would be the counting numbers. Plug in 1, then 2, then 3, then 4. But I need to start at 0, so I subtract 1 from that. And that way when I plug in 1, I get 0. Then I plug in 2, I get 1, and so on and so forth. Now on the bottom, it's even worse. These are the counting numbers, right? 1, 2, 3, 4, 5. But I need to start at negative 1, so I need to shift it over by 2 to the left. So it'll be 3 to the n minus 2. So if I plug in 1, I get 1 minus 2 is negative 1. That'll give me this one. When I plug in 2, I'm going to get 2 minus 2 is 0, and that gives me this one. And then it will continue. So this right here appears to be the formula, and we can just box that up and be done. Now the book might go a little further, so I'll show you what the book does on this probably. We could rewrite this as negative 1 to the n times 2 to the n times 2 to the negative 1 over 3 to the n times 3 to the negative 2. So I'm using properties of exponents that if we have the same base, different exponents, we add the exponents together. N plus negative 2 is n minus 2. So To put these two together, you would get this. We're going backwards. We're taking that, we're ripping it apart into its different factors. And the reason why we do this is because we can simplify this. This is just 1 over 2. And we can simplify this, which is 1 over 3 squared. And cleaning that up a little bit more, we get -1 to the n times I have 2 to the n. I have, let's see, what's this right here? It's 1/2 over 1/9. And then flip this up, that's 9/2. So 9/2. And over, sorry, I forgot to put this, over 3 to the n. And I'm going to go and do a little bit more. Since I have a 9/2, that's a nice constant. So a sub n equals this. A sub n equals, I'm going to bring the 9/2 out to the front. And then notice that the -1, the 2, and the 3 are all raised to the n power. So what I could do is I could put these two together, like this. I could go -1 times 2, all of that to the n. And then over this right here, 3 to the n. And since this and this are both to the n, I could go -1 times 2 over 3, all of that to the n power. And if I put this together, this is just -2/3. So I have times -2/3 to the n. And that's it. That's probably what the back of the book has. Now, we can check it. Let's just, for this first one, I'll check it. A sub 1 equals, let's see, if we plug in 1 here, we get 9/2 times -2/3 to the first power is -2/3. These 2's cancel, and we get 9 divided by 3, which is 3, but then there is a negative there, so we get -3. Go a sub 2, then we get 9/2 times -2/3 squared. That's 9/2 times, let's see, if I square this, I square the top, I'm going to get 4, square the bottom, I get 9. These cancel, I get 4 over 2, which is 2. And I can keep going. Let's see, let me do a sub 3. Would be 9/2 times -2/3 cubed, which is 9/2 times, now when you cube a negative number, it stays negative, so I'm just going to throw the negative out here. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And then we can clean this up. We have a negative, let's see, 9, 3, 1, 4. So we get 4/3. And I could keep doing this, but that matches up with the first 3 numbers that we had. And so that looks like we generated our sequence. All right. Let's look at number 6. So for number 6, we have the sequence 1, -1/3, 1/9, -1/27, 1 over 81, ... So I'm looking at these fractions, I'm getting an alternating sequence again. And it's a little different. This time I need to start with a positive, then go negative, then positive, then negative. So the way we do that is we take our -1 to the n, but we need to add 1 to that. If we add 1, then when we plug 1 in for n, we get 2. And that'll give us a squared. -1 squared is +1. Then when I plug in 2, I'll get a 3 up here, and that'll give me a -1. So that'll create the alternating we need. And then I'm going to look at the fraction. Looks like the entire time the numerator is 1. And then the bottom, these look like powers of 3. 3 to the 1, 3 squared, 3 cubed, 3 to the 4th. And that would mean this needs to be 3 to the 0. And on the bottom, you can't really see it here, but rewrite it as 1 over 1. And so you can match this up. 3 to the 0 is the bottom. Well, 3 to 0 is 1, so that does work. So what I need on the bottom is 3, and then I need to start at 0 and just count numbers. So n minus 1. All right, that would be good enough for me. You box that up, but let's try and take this a little further. This is negative 1 to the n times negative 1. So what I'm doing is I'm trying to get everything written out so I get powers of n on things so I can put them together. So what I do is I use the fact that this addition up here turns into this, right, because there's really a 1 there. And then you would add those two exponents together. Then I have times 1 over, and on the bottom, n, 3 to the n times 3 to the negative 1. And keep going here. All right, so the things that I have to the n are this, which is on the bottom, and then this, which is on the top. So I can rewrite that as negative 1 over 3 to the n. And then I have a negative 1 here over this. Now on the bottom, this really means 1/3. And since it's on the bottom, I flip it up as a 3. So I should have written this. Negative 1, that's this one. And then the 3 comes up. The 3 comes up. So that comes up. And one last thing. I'll put these two together and put them out front. So negative 3 times negative 1/3 to the n. Shall we check? If n is 1, you get negative 3 times negative 1/3, which is positive 1, which was our first guy here. If I go n is 2, let me see, n is 2, we get negative 3 times negative 1/3 squared, which is negative 3 times 1/9. So when you square that, you get 1/9. And then a negative times a positive is negative. That's good. The 3 and the 9 reduce out, and you get the 1/3. So this works. Let's look at 7. One half, negative 4/3, 9/4, negative 16/5, 25/6, ... Okay, we have an alternating sequence again. So let me take care of that first. Need to start it with positives, so I'm going to put n plus 1. And then let's take a look at the fractions. Well, the bottom is just counting numbers, 2, 3, 4, 5, 6, starting with 2. So to do that, I put n plus 1. That way when I write this counts by ones, 1, 2, 3, 4, 5, but I need to start at 2, so I add 1. So if n is 1, I get 2. If n is 2, I get 3. If n is 3, I get 4, and that'll create the bottoms. The tops, on the other hand, what do those look like? Well, you could say that this is 2 squared, but then this is not 2 to the 3rd power. So these aren't powers of 2 up here, but they all look like perfect squares. Like 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, and that means this first one would have to be 1 squared. So it looks like it's always a squared, so I always have a squared, but the base is actually just the counting numbers, 1, 2, 3, 4, 5. So if I put n here, n squared, that should do it. And in this problem, I'm not going to clean this up at all because I can't simplify like I did earlier, because in the earlier two problems, our exponents over here had n's in the powers. Here, there's no n's in the powers, so I'm just going to leave this expression just like this. I won't check it, but you can verify for yourself that that does work. Okay, what are we on? Number 8. Five, 8, 11, 14, 17, ... So what's going on here? Notice that each of these, it's just going up by 3 each time. Just keeps on going up by 3. So this first one is like 5. This one's like 5 plus 3. This one is like 5 plus 3 plus 3. This one's like 5 plus 3 plus 3 plus 3. This next one is 5 plus 3 plus 3 plus 3 plus 3. So each time I take a step into the next number, I keep adding another 3. And remember that addition, right? Repeated addition can be rewritten as multiplication. So this right here is the same as 3 times 2. This is the same as 3 times 3. This is the same as 3 times 4. And this first one right here would be the same as 3 times 1. So it looks like what I can do is I can take the number 5. So let me try and write my formula out. Take the number 5 and then add to it multiples of 3. I know that when I'm in my second number, I need to add 1 multiple of 3. When I'm at my third number, I need to add 2 multiples of 3. When I'm in my fourth number, I need to add 3 multiples of 3. When I'm at my fifth number, I need to add 4 multiples of 3. So it looks like if I put n here, it's not quite going to work. If I do n, because look, if I plug in 1, right, I'm going to get 8 and I need to get 5. If I plug in 2, I'm going to get 6 plus 5, that's 11. So I'm off. This is actually shifted over too far. I'm starting here instead of here. So what I need to do is when I plug in 1, I need to just get 5. And when I plug in 2, I need to get a 1 here. And when I plug in 3, I need to get a 2 here. So what I'm going to do is I'm going to shift this n minus 1 like that. And now when I plug in 1, I get 0 here. This all goes away. I get 5 here. When I plug in 2, I get a 1 here. That gives me a 3 times 1 is 3. 3 times 1 is 3. Add 5, we get 8. And then I keep going. And that's it. That'll work. I'm going to clean up. I'm going to distribute through. So 5 plus 3n minus 3. So we get 3n plus 2. Now, that's another thing, now that we see how clean this formula is, that's another thing we could have noticed from the very beginning. Let me show you. If I start this problem over in retrospect, if I write down all the multiples of 3, we get 3, 6, 9, 12, right, 15. Those are the multiples of 3, and I can create that using 3n. Each of these is just the multiple of 3 plus 2, right? Take 3, add 2, take 6, add 2, take 9, add 2. So if I just add 2 to each of these numbers, I should create this list. And like I said, going back and looking at it now and seeing this formula, this might have been easier to do, but would you have seen that right away? Probably not. You'd probably have seen that they keep going up. They keep going up by 3 on each step. So that's why I showed it to you that other way initially. All right, number 9. All right, for these, we want to figure out if these sequences converge or diverge. And if they converge, we're supposed to find out what they converge to. So in this, when they say converge, what I'm doing is I'm taking the limit as n goes to infinity of a sub n. So for this problem, it's the limit as n goes to infinity of 1 minus 0.2 to the n. And now just let n go to infinity. So what happens to this as we start raising it to bigger and bigger powers? So to help you see this in case you're having trouble seeing it, 0.2 is the same as 2/10, right? That's what 0.2 is, raised to the n power. So what happens if I plug in 1? If I plug in 1, get 2/10 to the first power, which is 2/10. If I plug in 2, so I'm letting n get bigger, this becomes 4 100ths, which actually got smaller than when I plug in 1. If I plug in 3, I get 8 over 1,000, and that's even smaller than this. So what's happening is as n gets bigger, this number right here raised to the n gets smaller. So what's happening is this is approaching 0. And so we have 1 minus 0, which is headed towards 1. So as n gets bigger, this expression, this sequence should get smaller and smaller. This one right here should get smaller, and so we should get something closer and closer and closer to 1. Remember, we're not saying we'll ever get to 1. We're just saying that's what we're approaching. So the answer is 1. It converges. So the answer would be it converges. And then what does it converge to? What's the limit? It's 1. Okay, 10. A sub n equals n cubed over n cubed plus 1. All right, so what happens here if we take the limit as n goes to infinity of n cubed over n cubed plus 1? Well, the top is getting bigger and bigger and bigger, right? The top is headed to infinity, and the bottom is also headed to infinity. And whenever we had that back in Cal 1, we used something called L'Hopital's rule. You can go look that up on my videos for Cal 1 if you need to, a review of L'Hopital's rule. But the problem that we have is that to do L'Hopital's rule, and I discussed this in my lecture, but I'll say it again. To use L'Hopital's rule, we rely on the derivative of the function. And we know that sequences are not functions. When we graph a sequence, it's dots. And so you can't talk about derivatives because derivative is a slope of a tangent line. And so we actually need a curve before we can talk about the slope of a tangent line. You can't talk about the slope of a tangent line at a single point if there's nothing else next to it, right? The next point's far away from it. So you can't get arbitrarily close and get that slope. So the derivative completely goes away, and so we can't use L'Hopital's rule. But there was a theorem that said if we do look at this limit and we replace our n's with x's, so we take the limit as x goes to infinity of x cubed over x cubed plus 1, where we're treating x as if it's a real number. What that means is we are looking at the graph of this thing as a function which draws a curve, realizing that our sequence, if we just do the ends, like plug in 1 we get this, and plug in 2 we get this, whatever the function does, the black curve, the sequence must also do. So it's a subtle thing here, but we have to convert the sequence into a function where we're allowing the variable to be in the real numbers instead of just the integers or just the natural numbers. Then we can apply L'Hopital's rule. So L'Hopital's rule says that if you have infinity over infinity, you can redo the limit and just take the derivative of the top over the derivative of the bottom, which in this case is the exact same thing. And then that just simplifies to be 1. And that's the answer. So whatever this does, according to the theorem I said in class, whatever this one does, this does the same thing. So the answer up here is 1. What you want to be careful to not do is you don't want to just rewrite this with just leaving your ends, because you can't use L'Hopital's rule on a sequence, if that makes sense. Hopefully it does by now. So, all right, let's look at number 10. Number 11, sorry. A sub n or you know, I'm going to write the limit now because that's what I'm going to be trying to do. Save myself some time. Limit n goes to infinity of 3 plus phi n squared over n plus n squared. All right, this is going to go in, we're going to do this the exact same way. If we let n go to infinity, we get infinity over infinity. That's where this is headed. So I'm going to rewrite it, replacing all of the n's with x's, and treating this as a function of x, where x is in the real numbers. And then I can apply L'Hopital's rule. Derivative of the top, 10x. Derivative of the bottom, 1 plus 2x. And this still goes to infinity over infinity. And so I apply L'Hopital's rule again. Derivative of the top is 10. Derivative of the bottom is 2. We get 5. So the answer to the original question is that it converges to 5. And keep in mind what we're saying. We're saying that with this original sequence, right here, if you were to list out the numbers, like if I plug in 1, let's see what I get. I get 8 on top, plug in 1 here, I get 2, that's a 4. And then if I plug in 2, I get another number, another number. What I can tell you is that the further out in this list I go, the closer and closer I get to 5. Without actually ever necessarily getting there, I can tell you that these numbers get closer and closer to 5 the further out I go. Right? I'm just trying to keep everything in perspective, like what it is we're saying here. Trying to determine where the sequence goes to. Okay, I think 12, well, we'll do 12. A sub n equals n cubed over n plus 1. Same thing, I get infinity over infinity when I don't have my limit in there. I should have written my limit. Let me do that. That's the original sequence. I got to remember to start writing limits on these. Limit n goes to infinity. This goes to infinity over infinity. So I rewrite it where x is a real number, x cubed over x plus 1. I'm going to apply L'Hopital's rule. Derivative of the top is 3x squared. Derivative of the bottom is 1. And now we get something a little different than what we've seen before. As x gets bigger, the top gets bigger, the bottom is just 1. So this is headed to infinity. And there's nothing else you can say about that. It's getting huge. So what we say is that this diverges. It's got to head to a specific number for us to say it converges. All right, 13. All right. So limit n goes to infinity of tangent of 2n pi over 1 plus 8n. Wow, okay, that looks different. So if n goes to infinity, the top here goes to infinity, and the bottom here goes to infinity. So inside here we're getting infinity over infinity. Well, we've done L'Hopital's rule in the past when we had that. So let me try this here. First of all, I'm going to rewrite this with x's, where x is a real number. And I'm just going to look at the inside. I'll come back and deal with tangent in a second. 2x pi over 1 plus 8x. If I do L'Hopital's rule on this, derivative of the top is 2 pi. Derivative of the bottom is 8. And that's just pi over 4. So what I'm saying is that as the x gets bigger and bigger and bigger, this thing heads towards pi over 4. That's what the inside of this is headed to, right? Because whatever this does over x, that's what happens over n also. So I know that the inside of this is going to pi over 4, which means that this is headed to tangent of pi over 4, which is just 1. So this sequence converges to 1. Do 14, then take a little break. Just a quick one. So limit n goes to infinity of 3 to the n plus 2 over 5 to the n. So as n gets huge, this gets big. 3 to a big number becomes huge. So this is going to head towards infinity over, and then 5 to a huge number becomes huge. This is infinity over infinity. So you're thinking L'Hopital's rule because that's what we've been doing. We actually don't need it here, and I'll show you why. Because both the 3 and the 5 are raised to the n power, I can rewrite the top like this. We did this earlier when we were trying to find the formulas. That's equal to limit n goes to infinity of 3 over 5 to the n times 9. So I put these two together into a single fraction. 3 squared is 9. And so I'm trying to figure out what happens here. Well, we saw this earlier when we did this, 0.2 to the n. We know that if the number in here is smaller than 1, then as you raise it to powers, it actually gets smaller, right? If I just look at 3/5 to the first power is 3/5. 3/5 squared is 9/25. And if you compare these two, this one is smaller than this one. And then as I keep going, it gets smaller and smaller and smaller. So as long as the number in here is less than 1, it's going to get smaller. And so this piece right here heads to 0. And then times 9, that doesn't really matter. The whole thing is converging to 0. So I did not need L'Hopital's rule for that. All right, quick break. Fifteen. Limit n goes to infinity, n squared over square root n cubed plus n. All right, so if we take a quick look at this, we'll realize that we get infinity over infinity again, right? As the top gets bigger, the bottom gets bigger. So you might be wanting to do L'Hopital's rule again. However, the derivative of this bottom piece is going to be pretty ugly, and I'm not quite sure I want to deal with that. So I'm going to use a different technique that we've used in Cal 1, and that's how can we turn this highest power of the denominator, which is n cubed, how can I turn that into a 1? Well, I can always turn n cubed into 1 if I divide by n cubed. So what I'm going to do is I'm going to be very clever here, and I'm going to introduce a 1 over n cubed right here. But I have to do it on the outside, so watch what I do. I'm going to do a square root of 1 over n cubed. And whatever I do at the bottom, I have to do the top. Like that. So this is a 1. And what happens here is since you have two roots that are multiplying together, I'm going to do the bottom first. These two roots become a single root, and then it's this times these two. So I'm going to distribute that through, but I'll do it on the next step. 1 over n cubed plus n, like that. Now on the top, this is a little more complicated, all right, because this kind of looks ugly. So what I'll do is I'll rewrite this as 1 over n cubed to the 1/2. That's what this is. And then I'll raise 1 to the 1/2, which is 1. And I'll raise n cubed to the 1/2. So I get 1 over n to the 3/2. So that's what the top is, multiplying those two together. And so I'm taking 1 over n to the 3/2 times n squared, which is the same as n squared over n to the 3/2. And then I subtract powers. 2 take away 3/2 is going to be 1/2. So the top is just n to the 1/2. Now on the bottom, what happens we have n to the 1/2 up top. On the bottom, when I distribute through here and here, I get 1, and then I get 1 over n squared. And so as n gets huge now, let's see what happens. N goes to infinity, the top goes to infinity, and the bottom, this right here, goes to 0. Fixed number over a huge number that gets really small. So I get 1 plus, oh, I forgot the square root. I get 0 here, I get 1 plus 0, which is 1. Square root of 1 is 1. So the bottom is headed to 1. We no longer have infinity over infinity. What we have instead is infinity over 1. And that heads to infinity. And so this diverges. So no L'Hopital's rule, just a clever usage of a multiplication by 1. And that's kind of a standard technique. So please be aware of it. 16. Limit n goes to infinity, square root n plus 1 over 9n plus 1. Now, when we take n and let n get big here, this top goes to infinity, the bottom goes to infinity, and then square root. So we have infinity over infinity. And whenever we've had that in the past, we've actually seen a couple of different things we can do. But L'Hopital seems good here because the derivative of this and this by themselves are pretty simple. Now, because we are going to use L'Hopital's rule extensively, and because we get tired of writing, switching this to x, I'm just going to write this down. This equals, by L'Hopital's rule, limit as n goes to infinity of, let's see, well, you know what? Let me be precise. I don't want to take any shortcuts here. Let me do this. I want to know what's happening to this, right? I know it's infinity over infinity. I'm going to switch everything to x first. X is a real number. And let me just look at this inside piece. X plus 1 over 9x plus 1. By L'Hopital's rule, this is going to go to 1 over 9. So that's going to 1/9. So I know that this is headed to the square root of 1/9, which is going to be 1/3. Just taking the square root of the top and bottom. So it converges to 1/3. Okay, next one, 17. Limit n goes to infinity of -1 to the n over 2 root n. Now this is the first time we've had an alternating sequence, and we're trying to figure out what happens as n goes to infinity. The problem that we're going to run into is that the numerator is not headed to anything. It keeps flip-flopping back and forth. It's going from 1, then -1, 1, -1, 1, -1, back and forth and back and forth and back and forth. The bottom, on the other hand, is headed to infinity. So what we're going to do is we're going to use a theorem that said if the absolute value of a sequence goes to 0, then the sequence goes to 0. That's a very nice theorem. So let's use that. Let me take this. This is my a sub n. Let's look at the absolute value of it. So what is the limit as n goes to infinity of the absolute value of -1 to the n over 2 root n? Well, when you take the absolute value of a fraction, you do the top and bottom separately, the absolute value of the top will always spit out a +1. Because no matter what this changes between positive and -1, once you hit it with the absolute value, it's just 1. So that turns into, this turns into the limit as n goes to infinity of 1 over, now the absolute value of the bottom you don't need because the square root of n will always be a positive number. So this is always going to spit out a positive number on the bottom. So I'm just going to write 2 root n. And it's pretty obvious what happens here. As n gets bigger, this thing goes to 0. And so if the absolute value of the sequence goes to 0, which it does, then the original sequence goes to 0. So the answer to this one would be it converges to 0. Just be careful on this theorem. The theorem says if the absolute value goes to 0, then the original one goes to 0. If the absolute value of the original one goes to something like 1, anything other than 0, then this theorem, you throw it out the window. You can't use it. All right. 18 looks like another one of these. So for 18, you have limit n goes to infinity of -1 to the n plus 1. That's an alternating sequence over times n over n plus root n. So what's happening here? On the top, it's getting big, right? This is getting big, but it's alternating between positive and negative numbers. And the bottom is going to infinity. So we almost have like an infinity over infinity, except for the fact that the top keeps switching between positive and negative. So let me see here. Let me try that theorem. What's the limit as n goes to infinity of the absolute value of this? Well, the absolute value of this piece right here is just going to spit out 1. So we have limit n goes to infinity of 1 times n, so that's n over root n. And then if you go through and apply L'Hopital's rule, I'm not going to show the work because now we're at infinity over infinity. You do L'Hopital's rule, that will turn out to be 1. And so you get that your answer is 1 here, right? Does that mean that this converges to 1? It absolutely does not mean that. because the theorem said that it had to go to 0. If the absolute value goes to 0, then that goes to 0. But if it goes somewhere other than 0, then it doesn't work. So what we know is this. We know that this piece right here, which really is constituted by this piece, that's headed to 1. So let me try and draw a picture of what's happening in this sequence. If this is 1 and this is negative 1, what's happening here is that as I go out further and further, this piece right here is going to try and force this ratio to be a 1. But this is going to switch it back and forth between positive and negative. So it's getting closer to 1, then negative 1, then 1, then negative 1. So if I imagine having like a horizontal line out here, the further I go out, my sequence is getting closer to 1, but then on the next step it'll be closer to negative 1, and the next step closer to 1, and then next step closer to negative 1, and it keeps doing this. So you're getting this scattered kind of, back and forth, and so you cannot say that this sequence converges. For it to converge, it has to go to one place, and this one, it is going to a certain number, but it's just the number positive and negative, and that doesn't work. It has to be one specific number. So this scattering of our sequence tells us that this thing diverges. You might be asking yourself, well, how am I supposed to write that down as an answer, Well, you just write down pretty much what I just said. Use sentences. Explain what's going on. All right, 19. Limit n goes to infinity, cosine n over 2. So as n gets bigger, we get infinity over 2, which is becoming infinite. So what does cosine do as you go out to infinity? So we know that the cosine curve looks like this. And since this is a sequence, it's just certain points on that, right? I don't even know where those points are, but... And I hope it's pretty obvious from this that the further you go out, that these dots, these black dots, are just going to be scattered all over the place. And they're not headed to one particular number. So this one would diverge. Now, what would happen, just for curiosity's sake, what would happen if I replace this with 2 over n? Now, that's a totally different function. So as n gets bigger, the inside goes to 0, and cosine of 0 heads to 1. So it would converge to 1 if that were flipped over. Just I will show you the difference. 20. Oh, how about that? That's exactly what they did on number 20. Hilarious. I didn't even look at that. I could foresee the future. 21 then. All right, so they give you the sequence in braces. So this is just a different way of defining the sequence. It means exactly the same thing as earlier. So that's what they write, and they say, does it converge or diverge? So what I'm saying is, if you erase the braces, and you put a sub n equals this, it's just the same exact thing. So what I want to do is I want to take the limit as n goes to infinity of this. So the top is a huge number, factorial is a huge number, infinity, and then infinity again. So you're thinking maybe L'Hopital. Well, the problem with L'Hopital is that in order to use L'Hopital, we had to convert this into a function of x, where x is a real number. Factorials are only defined when these are integers. So you're not allowed to let these be x's, because you can't do factorials of things like 1/2. At least not in this class we can't. So if these have to stick to being integers, we cannot convert this over to a nice smooth function. Hope that makes sense. So we're stuck. No L'Hopital's rule. So what we're going to use here are the properties of factorials. So how about this? We notice that the denominator, the factorial denominator is bigger than the one on top because it's n plus 1, or 2n plus 1 instead of 2n minus 1. So what I'm going to do is start peeling off factors. So the first factor of this would be this. Then I reduce it by 1, 2n. Then I reduce it by 1 again, 2n minus 1. And then I keep going down and down and down. But 2n minus 1, the rest of the way this way, is actually 2n minus 1 factorial. So these two now match and they cancel. And I think I'm going to have to get out of here. Look, what's my time here? 50 minutes. This will be perfect. Okay, so what I'm left with is the limit as n goes to infinity of 1 over 2n plus 1 times 2n, and that goes to 0. Are you here for the Cal 2 study group? No. Are you doing a study group?
Yeah, no, I'm sure I'll get that.
What time, 10? Okay, let me know. I'm going to try and work through a few more problems. Okay. This might be the last one I can do right now. 22. So we have limit n goes to infinity of arctangent of n over n. So arctangent of n, this gets huge over this, which gets huge. So I know the bottom is headed towards infinity. Question is, what's the bottom headed towards? I mean, the top. So arctangent of infinity doesn't really make a whole lot of sense. But what we do is we go back to the graph of tangent. Pi over 2, negative pi over 2. We dealt with this when we did improper integrals. We know tangent looks like this. And so when you say arctangent of infinity, you're saying where on the tangent function is the graph becoming infinite, going to positive infinity. And that's happening when you try and let the angle become pi over 2. So the top here has got to be headed towards pi over 2. And pi over 2 is a nice fixed number. And when you take a nice fixed number and divide it by a huge number, this thing goes to 0. So this converges to 0. All right, that's all I've got time for right now.